Look around you, everything seems solid and real. Tables, chairs, the screen in front of you. We trust the world is stable, that things exist whether or not we're looking. But what if this sense of reality is just an illusion? Physics, especially quantum physics, challenges our most basic assumptions. As we probe deeper, the universe appears less like a machine and more like a shifting landscape, shaped by our observations. Imagine a world that only becomes detailed when you interact with it, like a video game rendering new terrain as you explore. Could reality itself depend on our participation? This journey will reveal a universe far stranger and more mysterious than we ever imagined. For centuries, classical physics painted the universe as a predictable clockwork machine. Everything had a definite position and momentum, whether or not anyone was watching. Reality was objective and independent, like a billiard ball rolling across a table, its path certain even with your eyes closed. This worldview let us build bridges, launch rockets, and trust in the stability of nature. The laws of physics seemed absolute, describing a universe that existed with or without us. But as we looked closer, cracks appeared. At the atomic scale, the rules changed. The certainty of classical physics gave way to the strangeness of quantum mechanics. Suddenly, reality wasn't as solid as we thought. The universe was about to get very, very strange. The double-slit experiment. A cornerstone of quantum mechanics, it's an experiment that continues to baffle and inspire physicists to this day. It elegantly demonstrates the wave-particle duality of matter, challenging our most basic assumptions about reality. It shattered our classical expectations, forcing us to reconsider the very nature of reality at the smallest scales. The implications of this experiment are profound, touching upon the foundations of physics and our understanding of the universe. Fire electrons one by one towards a barrier. These tiny particles, the fundamental building blocks of matter, are about to reveal a surprising secret. One at a time through two slits, meticulously crafted in a barrier. Classically, we'd expect each electron to pass through one slit or the other. And you'd expect two bands on the screen, corresponding to the electrons that pass through each slit. A simple, predictable outcome, or so it seems. Like tiny billiard balls, each following a definite trajectory. This is what our intuition, based on the macroscopic world, would lead us to believe. But instead, you see an interference pattern. A series of alternating bands of high and low intensity. This is a hallmark of wave behavior, a pattern created by the superposition of waves, as if each electron is a wave, spreading out and interfering with itself. How can a single particle behave like a wave? This is the central mystery of the double-slit experiment, passing through both slits at once. It's as if the electron explores all possible paths simultaneously, a concept that defies classical logic. Each electron seems to exist in a superposition, a combination of multiple states at the same time. It's a blurry, probabilistic existence, unlike the definite reality we experience every day, taking all possible paths until measured. The electron exists in a state of uncertainty, a cloud of potential, until an observation is made. The act of measurement changes everything. It forces the electron to choose a single state, collapsing the superposition. If you check which slit the electron goes through, by placing a detector at one of the slits, something remarkable happens. The interference vanishes. The wave-like behavior disappears as if by magic. The electron acts like a particle again, passing through only one slit and creating the expected two bands on the screen. It's as if the electron knows it's being watched and changes its behavior accordingly. This raises profound questions about the role of the observer in shaping reality. The very act of observation, the act of gaining information, fundamentally alters the system being observed, forces it to choose a single reality, a single path, from the multitude of possibilities. This experiment reveals a universe at its most fundamental level, where particles are clouds of probability, existing in a state of potential, not solid objects, with definite properties and fixed locations. Reality at its core is far more fluid and uncertain than our everyday experience suggests. Is not fixed until we look, until we make a measurement and collapse the wavefunction. The double-slit experiment is a window, a glimpse, into the quantum world's deepest mysteries, challenging our understanding of reality itself. Our role as observers, as conscious beings interacting with the universe, is far more active than we ever imagined, shaping the very fabric of reality through the act of observation. The double-slit experiment, a cornerstone of quantum mechanics, leads to the observer effect, a mind-bending concept where the very act of observing changes reality. It suggests that the universe isn't a fixed, predetermined entity, but rather, before measurement, an electron exists as a wave of possibilities. A range of potential states, a superposition. It's in multiple places at once, in a probabilistic cloud. Measurement collapses this wave, forcing the electron to choose a single location, into a single outcome, a definite, measurable state. This isn't about human consciousness. It's not about the power of the mind. Any interaction that records information counts. Any process that encodes the state of the electron, the universe chooses a reality, selecting one possibility from many. The moment information is captured, the moment the wave function collapses. Quantum properties like position, things we take for granted in our everyday lives, or momentum, the measure of how much force is required to stop something, may not exist until measured. They are created by the act of measurement itself. At the quantum level, reality is participatory. We are active participants in shaping what we perceive, a dynamic process shaped by measurement. It's a dance between possibility and actuality. Our everyday experience hides this strangeness because we are dealing with vast numbers of particles. But at the smallest scales, where quantum effects dominate, reality is fluid and uncertain. It's a realm of probabilities, not certainties. The act of observation sculpts the world, like a sculptor shaping clay, from a haze of possibilities, from a quantum fog of potential realities. This raises a profound question, a question that has puzzled physicists for decades. If reality depends on measurement, what was happening before observers existed, before life emerged? Was the universe indefinite, a vast, unformed potential until something measured it, until the first interaction that recorded information? The quantum world challenges our deepest intuitions. It forces us to rethink our understanding of reality. We are not just spectators, passive observers of a pre-existing universe. We help create reality itself. We are active participants in the unfolding cosmic drama. To make sense of quantum strangeness, physicists developed the Copenhagen interpretation. It says, stop asking what particles really do when unobserved. Physics describes what we can measure, not what is. The quantum world is governed by probabilities, not certainties. Measurement bridges the quantum and classical worlds, collapsing possibilities into outcomes. The universe is fundamentally random. Chance is built into its fabric. The Copenhagen view works, but it leaves many unsatisfied. It avoids the question of why measurement matters, treating the observer as special. For some, this feels like dodging the real mysteries of existence. Dissatisfaction with Copenhagen led to wild new ideas. The Many-Worlds interpretation says every possible outcome happens in parallel universes. When you measure an electron, reality splits in one world, it goes left in another, right. Every quantum event creates new branches of reality. Another view, QBism, puts the observer at the center. Here, the wave function reflects your personal knowledge, not objective reality. Measurement updates your beliefs, not the world itself. Each observer has their own version of reality shaped by experience. Quantum mechanics becomes a tool for navigating uncertainty, not a description of what is. These interpretations make reality more participatory and subjective than we ever imagined. The universe may be a conversation between us and the world, not a fixed stage. Maybe the problem isn't just a missing piece of the puzzle or a gap in our understanding. Perhaps our logic itself, the very foundation upon which we build our understanding, may not fit the quantum world. We've been trying to force a square peg into a round hole, using tools designed for a different reality. Classical logic, the bedrock of our reasoning, dictates that things are either true or false, a simple binary choice. Something is either here or not here, existing or not existing, a definitive state. But quantum logic throws a wrench into this neat dichotomy, allowing for superpositions. These are states that are both and neither, existing in a probabilistic limbo until observed. It's a concept that challenges our fundamental intuitions. The famous double-slit experiment dramatically shows that particles can exist in multiple states simultaneously, a wave of possibilities, until the moment of measurement forces them to choose a single reality. Imagine a video game where a character is both safe and in danger, alive and dead, at the same time. This is until you interact with the game, until you make a choice. What if the universe's underlying code, the very fabric of reality, is written not in the language of classical rules, but in the strange and wonderful language of quantum logic, not in the deterministic clockwork of classical rules. This paradigm shift leads us to the ultimate question. If observation collapses the quantum state, who or what was the first observer? Did the universe exist in a haze of infinite possibilities, a sea of potential realities? Until something, somewhere, measured it, forcing it to coalesce into the reality we perceive? Standing at the edge of knowledge, we confront the profound mystery of existence, a mystery that deepens with every new discovery. And we begin to question our role, our influence, in shaping the very fabric of reality. The quantum world invites us to rethink everything, to challenge the assumptions we thought we knew, and to embrace the beautiful uncertainty that lies at the heart of it all.